So to continue this solution, at this point what I'm interested in predicting is the final speed of the package just before it strikes the deck of the boat. This package will be following along some sort of a parabolic arc like this as it falls down, and the boat's right inside of here someplace. So just before the package strikes the boat, it'll be traveling along some sort of a diagonal. It's going to have some horizontal component of the velocity, which hasn't changed. It's the same 86 meters per second that the package started with, Vx. And then I'll put this one as like V final. That's the final velocity vector there. But what I want to pay attention to is that as it falls down, the package goes faster, faster in the vertical dimension, faster. It's accelerating, going faster and faster, until finally, just before it strikes the boat, after 5.05 seconds, it's going really fast downward. So in order to figure out the final speed in 2 dimensions, what I have to do is add these 2 vectors together, the sideways vector, the x component, and the y component. So what that looks like is a right triangle, if I put them tip to tail like that, and then I can use the theorem of Pythagoras with this right angle inside of here to figure out what the length of this hypotenuse is. And the hypotenuse represents the final velocity. And since all I'm interested in, or all we're interested in, is the final speed, not the velocity with the angle right inside of here, just the length of that hypotenuse, that works out to be pretty simple. I can write it like this. I can say the final velocity speed, or the magnitude of the final velocity vector, is equal to the square root of the x component of velocity squared plus the y component of velocity squared. It's as simple as that. This one's 86 meters per second, and this is however fast the package is going downward after accelerating from rest for 5.05 seconds. Take a look at this. This is Vy equals V naught y plus gt. And since this term is 0 to start with, all we're looking at there is just gt. It's pretty simple. So I'll rewrite this. If I write it as just V sub f, or V final, without the vector absolute value signs, that represents the magnitude of that vector, so its speed, the length of that diagonal line. So I'll write this again clearly as Vx squared plus quantity gt squared. Cool. This is 86 squared. That's the negative 9.8 and the 5.05. So if I work out the details here and clickety-clack in the calculator, I come up with the final speed to be 99.2 meters per second. And that's how fast the package is going just before it strikes the boat. I'll write that as final speed. Great. Final speed. Alright, so now I'm going to work on the kinematics graphs. So I'm going to move my velocity diagram over here and then start creating the kinematics graphs. So in order to sketch the position, velocity, and acceleration graphs for the package, I've got to, of course, do it in 2 dimensions, 3 graphs in the horizontal dimension and 3 graphs in the vertical dimension. So create the graphical space, and then I just have to worry about labeling each part. So I'm going to start with the vertical position, the vertical velocity, and the vertical acceleration. And then below I'll put the horizontal position, and the horizontal velocity, and the horizontal acceleration. Now, I think it's easiest to draw the kinematics graphs for the horizontal position, velocity, and acceleration with a horizontal dimension first, because the definition of things in free fall is that gravity's only pulling downward on them, so they accelerate only in the downward direction. So there's no acceleration in the horizontal dimension. I'm going to try to get rid of that arrowhead and just draw the line segment here. See if that works. There you go. So 0 acceleration in the horizontal dimension, and then constant horizontal velocity, 86 meters per second. And then the position graph just is a line segment with positive slope, representing equal distances traveled in equal time, constant velocity. And now for the vertical dimension, the acceleration in free fall is always this downward directed negative 9.8, 0 meters per second each second. And then that corresponds to a velocity graph that has a negatively sloped line starting from v equals 0 to some final downward directed velocity. And the position graph, that's kind of fun to draw, I think, because it starts up here at some y naught 125 meters and falls down towards the boat's deck at y equals 0 meters. So these two videos have described the solution. And at the end, the final question, the final thing to consider is, what do we think about the rescue mission's plan? Is it reasonable to assume that if you're trying to save some sailors on a boat that's stranded out in the ocean, you could fly over sort of a low altitude flight, 125 meters, and drop a 50-kilogram package just the right point in order to let the package land on the deck of the boat? Well, my concern when I think about it is that the package, 50 kilograms, is about 2 pounds of weight per kilogram on the surface of the Earth. So we're looking at a 100-pound package or so, 110 pounds worth of package, and at 99 meters per second, that's on the order of 220 miles per hour. So when this 100-pound package of supplies hits the boat at traveling over 200 miles per hour, my instincts tell me that this isn't a rescue mission. This might have been a bombing mission where the plane's trying to destroy the boat. So in terms of planning a rescue, this isn't the plan that I would come up with. If I was planning to sink the boat, this would be an appropriate plan. But rescuing the people would not be smart. So to change it, what would I do? Make a lighter package. Make it so there's less mass in the package. Maybe it would do less damage to the boat. Or fly the airplane a bit slower. Fly it from a lower altitude. Or maybe even make the package float and have it land in near proximity to the boat, where someone could swim out and grab the food or fresh water or whatever the package has in it, and then wait for rescue. What fun.